Hi everyone. In this video, we're going to look at some examples where you're finding the derivatives of inverse trig functions. So these are the derivative rules, and you got a preview in class today of basically where they come from. But it is interesting that the derivative of inverse trig functions are not even trig functions. So you just need to study them, know them. Remember, though, that there are really just three main different rules that you need to remember. Because, for instance, inverse sine and inverse cosine basically have the same rule, except that the derivative of inverse cosine is negative. And remember that if the inverse trig function starts with a c, that's when the derivative is negative. Okay, so it kind of helps as far as remembering these. But let's look at some examples of how we would use these. Okay, so we want to find the derivative of the function. We've got g of t equals inverse cosecant of t minus 4 times inverse cotangent of t. So here we're really just finding the derivative of a difference. So we just need to differentiate each term and subtract, okay? All right, so if we want to find g prime of t, we're going to start with the derivative of inverse cosecant of t. So that would be 1 divided by the absolute value of t, and it would be negative because it starts with a c. So negative 1 divided by the absolute value of t times the square root of t squared minus 1. All right, and then minus. Okay, so this derivative, although we are multiplying 4 times inverse cotangent, 4 is just a constant multiple. So you can just bring that down in front of the derivative. Okay? So the derivative of inverse cotangent of t would be negative 1 divided by 1 plus t squared. Okay, and then we can, as far as cleaning this up, we're going to keep that first term the same. There's not much we can do to that. We could go ahead and multiply the 4, which is 4 over 1, times the fraction, and we end up subtracting a negative, so it will change to addition, and then we can just write it as 4 over 1 plus t squared. So it cleans up a little bit, but that's really about all we're going to do to simplify that or clean it up. Okay? All right, let's look at another example. So here we have y equals 5x to the 6 minus inverse secant of x. So again, to find the derivative here, we're just going to differentiate each term. So y prime would equal the derivative of 5x to the 6. We just need power rule for that. That would be 30x to the 5th power. Minus, and then we're going to find the derivative of inverse secant of x. So that would be 1 divided by the absolute value of x times the square root of x squared minus 1. And again, we're going to stop there. There's not, if we were to subtract, we'd be subtracting fractions. We'd have to find a common denominator, and then the question becomes, is it really getting simpler? Probably not. So it's best just to stop there. All right, let's look at this example. This time we have f of w equals sine of w plus w squared times inverse tangent of w. Okay, so this is going to require product rule because we are multiplying two functions. Okay, w squared is not just a constant. But we also have a sum, so we are going to differentiate each term. So let's do that. F prime of w would equal, now we're finding the derivative of sine of w. That's not an inverse trig function. That's a regular old trig function. So remember, the derivative of sine is cosine. So that's just going to become cosine of w plus plus, and now we have to do product rule. So we'll do first times derivative of the second. Derivative of inverse tangent of w would be 1 over 1 plus w squared. Plus second times derivative of the first. Derivative of w squared is 2w. All right, again, we'll clean it up a little bit, but not a whole lot. We'll keep cosine of w plus, we could go ahead and multiply. This would be like w squared over 1. So if we multiply straight across, we'll get w squared over 1 plus w squared. And then plus, now I would probably just move this 2w in front of inverse tangent, just so we don't confuse that as part of the angle of inverse tangent, or really if we don't confuse it as part of the ratio, because for your inverse trig function, the input is the ratio and your output is the angle. Okay, so anyway, I would just stop there, because to go any further, you'd have to find a common denominator, and it honestly would just get uglier. I do want to point out, however, though, you cannot cross out the w squareds, top and bottom, okay? Because you're adding in the denominator, so we're just going to stop there. Okay, now let's look at this example. Hopefully you're seeing that fraction bar, and so that's making you think quotient rule, okay? So we're going to use quotient rule here. So h prime of x will equal low d high. Now the derivative of inverse sine of x would be 1 divided by the square root of 1 minus x squared. So we have low d high minus high d low, which is just 1, all over low squared. Okay, again, we can clean it up a little, but not a whole lot. I would go ahead and multiply fractions in the numerator, because this is like 1 plus x over 1. So if you multiply that straight across, it'll be 1 plus x, whoops, 1 plus x divided by the square root of 1 minus x squared, minus inverse sine of x, all over 1 plus x squared. Okay? Again, if we went any further in our numerator, we'd have to find a common denominator and then multiply by the reciprocal, and then again the question becomes, is it even getting simpler? Now, I do want to point out, however, back to our original rule, you cannot cross out this 1 plus x and reduce it with one of these, because you are subtracting, okay, in your numerator. So you'd have to be able to factor out a 1 plus x from each term, from this term and this term, but we can't, it's not common to this second term. Okay, so the most that we're going to do is what we did in order to simplify it. Okay, I'm just trying to point out some common mistakes I've been seeing along the way. All right, and then let's look at this last example. So here we have y equals arcsecant, and remember that's the same as inverse secant, of 3x squared. So this is actually a chain rule problem, okay? Again, you can tell because the 3x squared is more than just x, okay? All right, so we're going to use chain rule here. Y prime is going to equal, now we're going to start with derivative of the outside. So the derivative of arcsecant is 1 divided by the absolute value. Now we're going to keep the inside the same, so it would be absolute value of 3x squared times the square root of 3x squared squared minus 1. So I hope you see that what I did there is I took the rule that we learned, the derivative of arcsecant, and basically just plugged in 3x squared in place of x. Okay? So that was finding the derivative of the outside but keeping the inside the same. But then we have to multiply that by the derivative of the inside. Derivative of 3x squared is 6x. Okay, so we can actually clean this up a little bit. We can multiply straight across and get 6x divided by 3x squared times the square root of 3x squared squared becomes 9x to the fourth minus 1. Now, the reason I was able to drop my absolute value symbol is because 3x squared is always going to work out to a positive number anyway. Because even if you were to plug in a negative there, you're going to turn around and square it, and it's going to become a positive. So we are okay to drop that absolute value symbol there. And then we can do some reducing with the 3 and the 6. That'll become a 2 in our numerator. And we can do some reducing with the x's. So we'll get rid of this x, and then we can get rid of one of the x's in the denominator. So in the end, this will simplify to 2 divided by x times the square root of 9x to the fourth minus 1. So yeah, we were able to clean that one up a little bit at least. All right, so those are a few examples. I tried to show you, how we can incorporate all the rules here. But we will practice this some more in class on Monday. I will see you